Hi there, in this video we're going to take the Taylor polynomial from the previous video and we're going to use it to derive the Euler identity, and then we'll have a look and see how that ties in with complex exponentials. So if we take the Taylor polynomial centred at the origin, then we can write the g of x0 equals the sum from n equals 0 to some value of I of the nth derivative of the function at x0 upon n factorial times the value, the function raised to the power of n. Okay, so that there is that's the one that we're going to use, and we're going to use that to derive the series for sin x, cos x, and we're going to look at the e to the ix, and we're going to see how those two are related. Okay, so we won't go through everything by minute detail because it's a bit tedious, and a lot of it's going to be work that you could work through yourself at some point. So let's look at a function. We'll try to find an approximation to the cosine function. So f of x is equal to cos x. So we know in order to find that approximation we have to differentiate it. Okay, so let's differentiate that function, and then we have to set the value equal to 0. So just go through the differentiation first. F derivative of x equals minus sin x, and second derivative of x equals minus cos x, third derivative of x equals sin x, and fourth derivative of x equals cos x. So we're back to the beginning. Okay, now we're looking at the derivative of the function at x equals 0, so put in x equals 0 for each of these, so you end up with cos of 0 is 1, sin is 0, cos from that instance will be minus 1, sin will be 0, and cos will be 1. Okay, so that allows us then to put the values of these in here. Okay, so we're going to end up with cos x, if I can squeeze it in this bit, cos x is going to equal, well, the first term is going to be 1 times, well, x to the 0 upon 0 factorial. Okay, so that's the value, that's 0 factorial is 1 plus, well, it's 0. Okay, so it's 0 times the second term is going to be 0 because we're multiplying with 0. Okay, so the next term is going to be the minus 1, so it's minus 1 times x squared upon 2 factorial. Okay, and then the next term is going to be 0, and then this term here is going to be, let's see if I can squeeze it in here, it's going to be 1 times x to the 4 upon 4 factorial. So we can write out, and if we'll just maybe do it down here, we can write out the Taylor series approximation to the cos x is equal to 1 minus x squared upon 2 factorial plus x to the 4 upon 4 factorial minus x to the 6 upon 6 factorial plus x to the 8 upon 8 factorial minus so on. Okay, so that there is the series that we're looking for. So that means that, to harken back to the last video, we can represent a complicated function cos x using a series of simpler functions. So that's a simple function because it's just a multiplication and a division and a subtraction and an addition. Okay, so we can generate that quite easily algorithmically. Now we can go through the same process with sin x, but I'm not going to go through all the details, so you can go through that same process with sin x, and you end up with x minus x to the 3 upon 3 factorial plus x to the 5 upon 5 factorial minus x to the 7 upon 7 factorial, okay, plus x to the 9 upon 9 factorial, and minus and plus, so on and so forth. Okay, so that then is the Taylor approximation for the sin x. Okay, and you can see here, it's quite interesting that cos x is an even function. Okay, so cos x is even, because if that's cos x there and that's minus cos x, then cos of minus x, that height there, is the same as cos of x. Okay, so that's an even function, and we've got even terms here, 2, 4, 6 and 8, and the sin x is an odd function. Okay, there's sin x there, because the sine of minus x, that height there, is minus the sine of x, which is that height there. Okay, and you can see that there, because sine here, we've got all odd terms. Now I'll just clean that off, or leave that there. So now we'll begin and we'll have a look at the complex exponential function. So what we're going to do is we're going to look at f of x equals e to the ix. So again, we can work through this. F of x equals e to the ix, and so we can have f derivative of x equals, it's going to be equal I e to the ix, and second derivative is going to be I squared e to the ix. Third derivative is going to be I cubed e to the ix, and I'll just get into maybe the fifth, okay, just to get this far down so we can get enough in. The fifth derivative, sorry, the fourth derivative is equal to I to the 4, e to the I ix, and f5 of x equals I to the 5 e to the ix, and again we're putting the value of 0 in here for x in each of these, so we end up with, well, I'll go through this first of all. Okay, so you're going to end up with, if you work through these, we have the I squared is minus 1, I cubed is minus I to the 4 is just 1, and I to the 5 is, again, it goes back to the value of I. So when we work through these and then we put in our values of 0 for each of them as well, we're going to get 1, and you'll get I, you'll get minus 1, you'll get minus I, you'll get 1, and you'll get I, and again you'll get minus I, minus 1, and you'll get minus I. So it just repeats in that fashion there. Okay, so when we put this into our equation, okay, their Taylor series, Taylor polynomial above, we're going to get e to the ix equals, again it's just a bit work, just put that in, put these values in, and we have it raised to the power x to the n, okay, divided by n factorial. So we just end up with 1 plus ix minus x squared upon 2 factorial minus I x to the 3 upon 3 factorial plus x to the 4 upon 4 factorial plus I x to the 5 upon 5 factorial minus x to the 6 upon 6 factorial, okay, minus blah blah blah, so on and so forth. Okay, so that then gives us the Taylor polynomial, Taylor series for e to the ix. Now, turns out when you look at them, and it's an excellent little bit of maths, that this here is related to these two via an identity, and you can see that, and I'll write it out just in kind of a long form. We can write, I'll just rewrite these out so just so it becomes obvious. E to the ix equals 1, I'll do the cos x one here in unison, and also the sin x, so that equals, well, the cos x is, that's 1 and that's 0. Now the next one is plus ix, and that's plus 0, and that's plus x. Okay, the next one is minus x squared upon 2 factorial. Other one is minus x squared upon 2 factorial and 0. Okay, and third one is minus ix cubed upon 3 factorial, and that is 0, and that is minus x cubed upon 3 factorial, and the next one, I'll just do this next one, that'll be us, okay, that'll be plus x to the 4 upon 4 factorial, that's plus x to the 4 upon 4 factorial, and that is 0. So the identity becomes apparent because you can see that e to the ix equals, well, it's this one here, so that's 1, well, you can see this right, that's 1, so that's that one there. Now that's x, but it's times I, okay, and this one here is equal to that one there. This one here is equal to that one there, but we've got to multiply by I. And this one here is equal to that one there. So it turns out, if you look at it, it's equal to cos x plus I sin x. So there's a cos x bit there, so that's a 1 and 1. You can see the cos x there as well, that's equal to that. And you can see the I sin x, so it's sin x, which is minus x to the 3 from 3 factorial, times I, okay, so that's how the factor of I in there and multiplying together. And you'd see that again as you work further up, okay, so that there is the Euler identity, and the more kind of famous way of writing it is to notice that if we put in a value for pi there, we get e to the I pi, that equals minus 1, okay. So that there is the famous Euler identity. Now, the point in doing this here is really for us to get to this point here, and this is when the nomenclature will change a little bit. We'll change the x, we'll change that to theta, okay. So these values are just in radians, okay, and really just, as we tend to be drawing circles and phasors, we tend to be talking about angles in terms of theta historically, okay. So we'll just replace x with theta, and also the complex number I, imagine number I we'll replace that, and instead of calling it I, usually in electrical engineering, terms we call it J. Okay, but it's just the same thing. So really we can write out then, we could say e to the I theta equals cos theta e to the j theta, so e to the j theta equals cos theta plus j sin theta. Now we can come up with a couple of trig identities as well from that. Okay, so we could note that and we could write the if we wanted to, we could write that as e to the minus j theta, okay, would equal e to the minus j theta would equal cos of theta minus j sin of theta, just because cos of minus theta is the same as cos of theta, and sin of minus theta is the same as minus sin theta. Okay, now we can take these two identities, identity 1 and 2, and we can also note the identity from these two here. You can just change them about to find out what cos theta is in terms of this, and what sin theta is in terms of that as well. So you end up with e to the I theta plus e to the minus I theta upon 2 equals cos of theta and e to the I theta minus e to the minus I. It's actually j. Keep forgetting about that. I mix up i's and j's depending on what I'm doing. So all upon 2j equals sin of theta. Now you can see these two quite simply if you were to draw this one out in a complex plane. So that's a complex plane, and that's the real part, that's the imaginary part. Now this phasor here, we can think about this as rotating in the anti-clockwise direction, so that's e to the I theta. Okay, so that's how it's defined it's purely by definition that that's rotating in that direction. And the other one would be e to the minus I theta, j theta. Again, that would be rotating the opposite direction, e to the minus I theta. And when you add both these together, they add up. Vectorially, so that comes over to there, that comes over to there. So you can see these two as they swing round about, in unison, they will map out this axis. Okay, and you can see because there's two of them, we've doubled the distance here, so we'll need to divide everyone by 2 to get back to the original value of cos theta. So the cos is this line here. Okay, and the same thing will happen with the other one, which is the sine of theta. Okay, so that's the imaginary part, that's the real part, and again we're going to have e to the j theta that way, and that's e to the minus j theta, but it's not e to the minus j theta, it's minus e to the minus j theta. So again we just change that, okay, because it's just a vector, so the negative of a vector is just a vector pointing in the opposite direction, so that's that vector there. Okay, still going in the same direction from there. So taking these two vectors, and they're rotating as phasors, they're rotating in opposite directions. So as to do that, we can, there's some space there to get that down. I can't actually get down the bottom, but we add those vectorially the same as we'd add these ones vectorially, only the vectors are pointing down this direction here. Okay, and it means we map out, we're going to map out this line here, okay, which is the sine theta line. And again, we've gone the direction of twice as much because there's two of them, so we have to divide them by 2, and to get rid of the complex term we'd have to also multiply by the j. Okay, so that's how you end up with e to the 2j, and that's sine theta. So these here are complex exponentials, and so the e to the I j theta represents a phasor rotating in the positive, in the anti-clockwise direction, which is defined as being the positive direction, and e to the minus j theta is a phasor rotating in the clockwise direction, which is defined as a e to the minus j theta. Now, what you have to understand, and it's something I never really appreciated when I first seen this, was that this here is the real number line and that's the imaginary number line. Okay, so this is not like saying we have a function x and y, and we have cos and sine, and the cosine and the sine map out a circle. Okay, you're not quite saying that, because this plane here that we're looking at here is, well, it's a one single line, which is your independent variable. So your independent variable is a single line, it's the real number line, and your dependent variable is your value of y. But that's not really what we've got here. Haven't got just one line of numbers, we've got a plane of numbers. Okay, and the exponential function at e to that j theta, the e to j theta maps the real onto the imaginary in such a way that it maps out a circle or a rotating phasor. Okay, and that's completely different. But that's different from having a real number line mapping through a function to another real number line. That's not what's happening in this case. Okay, the whole plane that we're looking at here are all our numbers, the whole plane there, even in fact you say, is the independent variable. Okay, so that there is not the same as that there, although in the end it looks the same. But remember, in this instance here with the imaginary number line, we've got an I or a j in front of this part here, so that's quite important, and something that you tend maybe not to notice when you first come across it. So that's all about complex exponentials. So it means we can represent a complex exponential in the form of re to the j theta, where r is the length of the vector, okay, and j theta, the fact that it's positive, tells us that the phasors are running in the anti-clockwise direction. Okay, and they're related, and you can see it's a phasor because rotating and mapping out a circle because of the Euler identity, which is e to j theta is cos theta plus j sine theta. So that's where the complex exponential comes from. Now the next video we'll go on and we'll start looking at the Fourier series, and we'll derive the Fourier series, but we'll derive the Fourier series from the standpoint of a vector space and an orthonormal vector space, and that's the best way, I think, to go through that derivation. Anyway, we'll get in the next video. Thanks for listening. Goodbye.